G'day, ladies and gentlemen. We have another problem here. The couple moment is applied to a beam of a cross section shown in a plane, forming an angle beta equals to 75 degrees with the vertical. Determine the stress at point A, B, point B, C, point D. Now this is our image. This is a moment, 8 kilonewtons. First thing we'll do is, since this is coming off the y-axis and this is 75 degrees, we'll just minus that from 90 and we'll get 15 degrees. We're going to assume, and we're going to state that this is the positive direction for z and this is the positive direction for y. And then the formulas we're going to use are the moment of inertia formula, which is going to be 1 on 12 base times height cubed plus area times distance from the centroid squared. However, since we're using the vertical here and it is a perfectly rectangular shape, we will not be utilizing an AD component of this formula. And then we're going to determine the stress, and the formula for this stress is negative moment about z multiplied by the vertical distance from the centroid to point y divided by moment of inertia z plus moment about y times horizontal distance from the centroid to a point z divided by moment of inertia y. Now first thing we'll do is we'll find the distances. Now the way easiest to do that is to draw an axis up and down, and then we look at the first component on the y-axis, A. So since this is going up the y-axis, YA is positive. Then to the right is the B, but it's also coming up from the centroid, YB is positive. And then D, you have to go down on the axis in the negative direction. That means it's negative YD. And all of them had to travel a distance of 0.03 meters, which is just half of 60 millimeters. Now similar for Z, we had to travel in a positive direction, 0.06 meters to get to A, so ZA is positive. Then in the negative direction for B and D, so negative ZB equals to negative ZD, all equal to 0.06 meters. Now to find moments, just trig. So moment for Z in this direction, there'll be sine 15 multiplied by 8,000 newtons. Opposite over hypotenuse, because we're calculating the opposite. And y will be cos 15 times 8,000, which will give us that value for the moment. And those values will be 2070.55 newton-meters and 7,727.4 newton-meters. Now to find the moment of inertia is a slightly tricky one because it's a hollow. It has an outside diameter and an inside diameter, or distance, inside distance, outside and inside distance. So, and since it's not a solid, not a filled in shape, we have to, for in moment of inertia about Z, 1/2 base 0.12 times height 0.06 to the power 3 minus 1/12 times 0.1 meters times 0.04 to the 3. And that will give us just this outline here, the moment of inertia at Z, just for that outline. Similarly for moment of inertia at Y, 1/12 multiplied by base, in this case this is the base, times height to the power 3 minus base times height to the power 3. And those two moments of inertia for I, Z, will be 3.06 times 10 to the negative 6 meters to the 4. And IY, moment of inertia for Y, will be 5.306 times 10 to the negative 6. Now all we need to do is just put all these values together into this formula in order to get our stresses at point A, B, and C. So all we're doing is, stress at A is the moment at negative, moment at Z, multiplied by Y, A, which is positive, so it'll be 0.03, divided by moment of inertia at Z, which is here, plus moment at Y multiplied by horizontal distance, which will be positive in this case as well, divided by moment of inertia at Y. And then as indicated in its formulas. And what we'll get is the stresses at A will be 67.08 megapascals. Stresses at B will be negative 107.7 megapascals. And stresses at D will be negative 67.08 megapascals. Thank you very much. I hope that helped.